Yeah, I thought maybe I would just kind of overview, I guess, chapters 5, 6, and 7, even though we didn't read 5 and 6. Well, not saying much about 5 because we actually did talk about that a little bit last time. And in the process, describe some of the questions I got over the last couple of weeks about things that were confusing to people. Since I'm sure if it was confusing to one person, it's got to be confusing to more than one. Yeah. So and please interrupt with questions at any point. So yeah, chapter 5 talks about the Fiat-Shamir transformation. I mean, at a high level, and this is really all I want to say about this week. This is just a generic transformation from interactive public coin protocols. It just removes the interaction from them. So it'll take your interactive succinct argument and make it a snark. For example, well, an interactive succinct argument of knowledge, if you want the K in snark. And just pull out the interaction. And roughly speaking, if you don't really care about details of provable security and stuff, it'll just preserve the security of the interactive protocol. Now, there's a bunch of results kind of scattered throughout the book about actually establishing that security is preserved. Yeah, in various contexts, and most of those proofs operate in the random oracle model, which in the world of theoretical cryptography is a little bit controversial because it's an idealized model that sort of imagines that cryptographic hash functions just sort of are indistinguishable from truly random functions to polynomial time adversaries, which is not like actually the case in the real world. But practitioners are very happy typically with security in the random oracle model. And there's discussion in chapter 5 about sort of what's known about the security of the Fiat-Shamir Transform protocols in the standard model. Yeah, so that's really all I wanted to say, I guess, about Fiat-Shamir. I think I mentioned 2 weeks ago very briefly, there was a bunch of deployed snark implementations had an issue with how they implemented Fiat-Shamir. It was actually a previously known issue that led to vulnerabilities in systems years ago already. It comes up the vulnerability sort of comes up in contexts where the adversary itself, like the cheating prover, gets to choose the statement that it wishes to prove. But that is this is when you want security against that setting, it's called adaptive security. And this is actually the case in like public blockchain settings where people are claiming to know they're claiming to know digital signatures or secret keys or something, and they get to choose the signature they claim to know and so forth. So the chapter does talk about that, and I thought I would just keep mentioning that since it's a known issue, so it'd be good if we sort of stopped the issue arising over and over again. Okay, so that's chapter 5. Did anyone want to ask any questions about that?
You said this was a known issue before it was disclosed as vulnerabilities in these few implementations, right? So people.
Well, what I mean is, I don't mean that it was like known that these particular snark implementations had the issue. So what I meant is there were previous cryptographic systems, like for example, this came up in the Helios voting scheme, where it was the same underlying oversight, like years ago, that made the same sort of misconception or just oversight made its way into these snark implementations, as well as into some of the theoretical papers that the snark implementations were implementing. Yeah.
Mm-hmm. Thanks. So I mean that's not really very related question, but for someone who's just implementing protocol, like is there? I guess there isn't really a list of like, okay, here if you're implementing protocol X, here are the kind of previously known exploits or issues found with that. Beware, right? You just kind of have to do your own research on every specific protocol and see what's been broken in the past?
Yeah, I mean,
It's a very broad question,
right. Yeah, I'm not sure I'm really the best person to ask about that. But I'm not aware of, like a compiled list of like, if you're implementing snarks, here are like the various pitfalls that have happened like more than once or something, to be aware of. Although that would be useful. So obviously this Fiat-Shamir issue is one. I don't know. There are some like there's just been prominent bugs that if people who have followed the space know about. There was like the Zcash issue where they included extra elements in the structured reference string that actually more or less would have allowed somebody to like undetectably create Zcash out of thin air or whatever for years. And the book discusses that issue as well. Things like that.
If I could add a bit of context, it was my interpretation that the Fiat-Shamir attack on the several zero-knowledge circuits that were vulnerable to what was described as, I forget what they called it, frozen heart. It was because the Plonk authors had sort of made an implicit assumption about their readers' capacity for writing Fiat-Shamir, like everyone kind of knew what it was. So they gave a very implicit description of Fiat-Shamir, which did not include recursive using like the output of each random oracle query and the input to the next random oracle query. So a lot of the implementations didn't include that and were vulnerable to exactly the attack that was described.
Yeah. Let's see. I mean, I don't know much more detail than that. So that sounds plausible. Like again, this issue it had arisen before, in like the cryptography community. Fiat-Shamir is used all over the place. So in these research papers where authors are just publishing their result, they're not necessarily paying as super close attention to like writing down a there's description of how Fiat-Shamir should be implemented, and that can, if then implementers just sort of directly implement, their best understanding of what's described in a research paper, that can be problematic, I guess.
Yeah, it sounds like that's what happened.
And sure, yeah, I know that I've seen, another common issue that happens all over the place, not just in snarks, is people will use non-cryptographic pseudo-random number generators in cryptographic contexts, like a Mersenne twister or something. That's no good. So that's something to be aware of in any cryptographic context. That's going on. There's discussions about stuff like this, I know, in like Linux now and stuff. But yeah, I don't know that anyone's compiled a list of like, here are like the top 10 things to avoid security bugs in snarks that, that would be probably useful.
I'm going to post a thing in the chat called Lee-Lim primes, which apparently there have been like lots of very bad choices of how to generate your primes. There are only a couple of good ones. And I think one of the good ones is called a Lee-Lim prime. So worth a rabbit hole.
Okay, so that is Fiat-Shamir. Obviously, if you want more details, feel free to check out Chapter 5. Okay, so Chapter 6 is about what I call front ends. So these are techniques to kind of take a description of like the computation that you actually want to sort of the statement that the prover wants to prove. And turn it into a what's typically called an intermediate representation. So this is the kind of statement that snarks that we design are actually capable of handling. And typically, this is some version of circuit satisfiability, R1CS satisfiability, or now you'll hear a lot about things like, Zcash. The Zcash folks coin like Plonkish arithmetization, which is just like various variant IRs that, some of the backends kind of prefer to use or capable of using. So I wanted to say a little bit about that chapter, and I guess how it because then like sort of the rest of the book focuses on snarks for circuit sat or R1CS satisfiability, and I got some questions about sort of the relationship between the two. So let me couch this in a specific example application, since I think that'll help clarify some of the confusion that was getting expressed to me. Imagine that the prover, wants to prove, there's some hash function, say SHA-3, and some output of SHA-3, just some value. And the prover wants to prove that it knows a pre-image under SHA-3 of that value. So you wind up with, people use different terminology for that pre-image. So some people will call it the witness. It's the object that the prover wishes to establish that it knows. Some people will call it the prover's private input. Let me call it the private input because as we're going to see in a moment, this is what I want to clarify. It winds up being sort of a terminology collision when you turn it into a circuit sat instance. Okay, so yeah, the prover's goal is to prove it knows a pre-image of this hash value. Let me call the hash value, I don't know, Z. Let's say Z under SHA-3. So you would typically what you would do is you would write like a computer program that takes as input the pre-image and evaluates SHA-3 on it. You would write a computer program in some language to do that, and you would feed that program through your front end. Okay, and that front end would spit out a circuit satisfiability instance that is equivalent to the claim. And what that means is the circuit. Okay, so now I'm going to use the whiteboard. So yeah, so the prover claims to know. I think I use for, let's say, an L such that H of L equals Z. That's what the prover claims to know, L. And this gets turned into a circuit satisfiability instance. Now, I'm going to simplify notation compared to the book. I'm just going to say, so the circuit, the front end spits out a circuit C such that there exists a W. W is the input to C, satisfying. Let's say C of W equals 1 if and only if there exists an L such that H of L equals Z. And moreover, because this kind of claim is a claim about knowledge soundness, the prover knows an L, and there was discussion in the chat about how standard soundness is like trivial here. If the hash function is surjective, there always exists such an L. So the only interesting question is, does the prover actually know L? So moreover, if P knows W, then P also knows L, right? You can go from like W back to L, and also you can go from L to W, but we don't actually need that direction. P knows W, then P knows L. So the circuit sat witness sort of contains L, the object that the prover is claiming to know, in like the original claim. But in general, W might have more stuff in it other than L. Okay. So let me clarify some things, I guess. So in the book, there was a public input X. So what I said was there was a public input X to the circuit satisfiability instance in addition to W. And the claim was just everything was the same other than this C of W equals 1 would just became a C of X comma W equals 1. Okay, so I guess the first thing I want to do, so I was basically getting questions about, in the circuit satisfiability instance, what are X, what are W, and how do they relate to sort of the object L that the prover is claiming to know in the original application, which I now want to call the private input instead of the witness, so that there's not this sort of collision between calling both L and W like witnesses. Even though they both are witnesses in a certain sense, so that's why there's a collision if you're not careful with the terminology. So this X is just something that's known both to the prover and the verifier, and like in this context, what X might be might be like an initialization vector for the hash function or something. So it's like the circuit C might, for SHA-3, I think this is really getting deeper into the weeds of applied cryptography than I really go, but I'm pretty sure in like when SHA-3 got standardized, there's some initialization vector that just got fixed in that standardization process. So when people say SHA-3, like they've kind of fixed this initialization vector, and so SHA-3 is just like a deterministic function now. But you could imagine, that the circuit C is actually capable of computing SHA-3 with any initialization vector, and this input X is just telling the circuit, hey, this is the initialization vector you should use. So it's, in particular, this X is like, it's just part of the statement that the prover, needs to, is claiming something about. So to get a complete description of like, what the computation, the circuit C should be doing, it's like C is, there are applications where C needs to take this public input X to like just finish describing like the work that the circuit C should be doing. Okay, so I wanted to say that to clarify how you should think about this public input X, because I was getting a lot of questions about that. And then I wanted to say a little bit about, why does this witness W for the circuit sat instance contain like more stuff in it than the private input L? Okay, and the answer is to support like efficient, like to make the circuit small, it's helpful. It turns out to be very helpful to allow, people will often call them advice inputs to the circuit. So the chapter 6 in the book, somewhere in that chapter, I know I put in discussion to try to make this nice and concrete and simple. You could imagine a computation that does a lot of division operations. Okay, and if you actually did not allow any sort of extra advice inputs to the circuit C would have to like literally compute division inside it using like the extended Euclidean algorithm, right? Like this is happening sort of everything's in a finite field, and if you want to know what is 100 billion divided by 16 or something, it would literally have to run a division algorithm. Okay, but when you allow advice inputs, the circuit you sort of so this witness W to the circuit, you could think of it as it sort of starts with the private input L that the prover is claiming to know, but then you let it take extra advice inputs. And for this division example, the device inputs might be for each division, just stick in there the result of the division. So like if the result of the first division is A1, stick A1 in there. The result of the second is A2, stick A2 in there, and so forth. And it's like a guess and check situation now. So rather than the circuit having to compute the division from scratch, you let the advice inputs sort of just tell the circuit the answer to the division. And so like the untrusted prover is going to stick these advice inputs in there. And then the circuit just has to check that the answer is accurate. So rather than computing A1 from scratch, now it can just check that, if A1 is supposed to be, E over F, right? The circuit can just check that, sorry, my hand is screwing up the whiteboard. The circuit can just check that, what would it be? What is it? E equals F times A1. I think I did that right. E over F equals A1 if and only if E equals F times A1. And so the point is, like, rather than computing a division from scratch, which requires like a long it's like that's horrible to put in a circuit, you know, over a finite field. Now the circuit's just doing one multiplication to check that, you know, the advice input is indeed the correct answer to that division. So conceptually, you know, that's, I don't know why I didn't have this problem last week where as I was, like, you know, zooming in and out, this is like my browser is just doing all sorts of funny things. All right, hopefully, anyway.
So is every element of W considered private input then, like A1, A2, and these extra inputs?
So if you so I was using private input in this discussion, this verbal discussion, to refer just to L, which is like, you know, sort of the witness for the original statement that the prover is making. You know, the prover is claiming to know something, know some object. And so I was using the term private input to refer only to that. But if you're asking about like zero knowledge, you know, so are you saying like, is all of these advice inputs, are they private in the sense that, like, you know, if you release them to the verifier, they'll leak information about L? The answer is potentially they will leak information about L. You certainly can't rule it out because, you know, they're like determined by, you know, like these divisions that are getting done by the circuit, like the answers are somehow determined by L, and hence these advice inputs can contain some kind of information about L.
Got it.
Yeah.
So W, the witness, is basically the private input L plus these advice inputs.
That's exactly right.
Yeah. Okay. Thanks.
And so I probably need to say something somewhere in the book, whether it's 6 or 7, chapter 6 or 7, or both, to clarify that, because, you know, I confused the heck out of some of you. You know, about, you know, well, you know, what is this W that we're calling the witness, and like why, you know, yeah. So in chapter 6, it describes like completely generic transformations from, like, you know, like a computer program that runs in T time steps, and, you know, takes as input L, and, you know, applies H to L and checks if it equals Z or something like that. It describes like just a totally generic way to turn that into an equivalent circuit satisfiability instance of size somewhat close to T, you know, T polylog T. And in that situation, the advice inputs are actually just an entire like execution trace of a random access machine, that simply, you know, applies in this context. It would, you know, the random access machine would take as input L and compute H of L, and, you know, check does it equal Z. And in that very generic transformation, the advice input is literally just like a step-by-step description of what that random access machine did over the course of its computation, and the circuit just checks that that execution trace of the random access machine is like valid. But like in practice, people, those transformations are quite expensive, even though people are using things like them. But I mean, they are paying a price for them. So in practice, you know, people are often like sort of hand designing circuits, and then the advice inputs might look a lot like what I described, where, you know, there are these multiplicative inverses that you can think of as just like the answers to a bunch of division operations. You know, they're not, when people are handwriting circuits, the advice inputs are not necessarily like actually an execution trace of a random access machine. That's just the totally general technique described in chapter 6 of the book. Let's see, do I want to say anything else? Maybe that's enough. So the book sort of walks through kind of, I'd say the main techniques and ideas that have gone into various front ends. But, you know, the work on these front ends that, you know, spit out circuits or R1CS or Planckish arithmetizations or whatever from computer programs is like some, vast research area. And so putting it all into one chapter, I can only say so much. Maybe it would be helpful if I sort of say a little bit about what some of the roll-up projects are doing now in this context. So, like Starkware right now has taken the approach of, so their front end is called Cairo, and they have some high-level programming language, and they sort of use techniques like very related, as far as I know, to these generic, like take a random access machine and have the advice inputs be an execution trace of it, and have the circuit like check step by step that execution trace is accurate. So that's kind of what Cairo is doing. Now there are details that I'm not getting into, like I believe that they use a slightly different, intermediate representation. They call AIR, algebraic intermediate representation. It's sort of tailored to their backend. We don't have to get into those details. There are other projects where the sort of the high-level language that is exposed to the programmer or the the user of the network or whatever is just Solidity. They want to support general Ethereum virtual machine, and so the front end maybe then has to do more work. It's like a more challenging sort of compilation problem because the high-level language sort of was not designed with like snark friendly front ends in mind, the way Cairo just sort of used off the shelf techniques with some optimizations. So maybe and as far as I know, they're still well, I know ZK Sync released their they're generating circuits from their testnet, but I don't think they're actually generating proofs right now. Anyway, so yeah, that's just some of the things people are doing in practice with these front ends right now. And yeah, so maybe that's helpful for those interested in sort of what people are doing in practice. And hopefully I've now clarified how people should think about this W that's getting fed into the circuit satisfiability instances and like, the entire rest of the book, and how it relates to the actual claims provers might be making in practice, like knowing the pre-image of some output of a hash function or something. Yeah, okay, so that was my chapter 6 ramblings. Any questions?
So the configuration graph thing that was mentioned was just theoretical, right?
Yeah, and I believe the configuration graph discussion in chapter 6 was before we got to circuit stat. It's when we were just turning deterministic, random access machines or Turing machines or whatever into circuit evaluation instances. And those transformations in general are like when you don't allow. So when you're dealing with circuit evaluation, meaning we're not introducing these, basically no advice inputs to the circuit. So in general, those transformations, if you're not allowed to use advice inputs in your transformation, in general, it's terrible. It's like truly awful, in the sense that you can take a computer program that runs in time t and space s, where in general s might be as big as t, right? Like a very space intensive machine, might sort of use as much space as time. And the best transformation, known and probably possible in that context would actually result in a circuit of size t times s. So in the worst case, t squared, is totally impractical. Now, of course, to be clear, there are computer programs that are very amenable to implementation in circuits. Like, the simplest example might be like naive matrix multiplication is an n cubed time computer program and has a circuit of size n cubed, right? It's just naturally a circuit. But in general, you take an arbitrary computer program that runs in time t and uses space close to t, and you can't turn that, unless you have the ability to have advice inputs, you just can't turn that into a circuit of size smaller than like t squared. So yeah, the configuration graph thing in chapter 6, if I remember right, because I haven't looked at it in a little while, that was in the context of the circuit evaluation instances, so no advice inputs, and it was pointing out basically that like you could get decently small circuit, or at least low depth circuits or whatever, for small space computations. You know, if you run in like a very large amount of time, but only a small amount of space. But nobody is actually using a configuration graph of a Turing machine to write down a circuit in practice now. Yeah, that's just a sort of an asymptotic theoretical kind of treatment there. Yeah.
Oh, okay. Thanks.
Yeah. Yeah. In the practice of snarks, people are, they're always going to use the advice bits. The cryptography sort of gives you fairly efficient support for them. And they let you make your circuit, typically like vastly, vastly, vastly smaller. So it's like a win you're going to want to make use of them. So, the whole start of chapter 6 that, doesn't talk about circuit SAT, but talks about circuit evaluation is sort of meant for conceptual purposes and not, no one in Snarkland is not using the advice bits. Okay, any more questions? Should I go on to chapter 7? Cool, all right. Yeah, so chapter 7 gave our first snark for circuit evaluation. I'm now going to describe it, I'm going to summarize it, and for simplicity, I'm going to continue to cut out this public input X, that appeared in the book, and just say, the prover claims, to know a W such that, let's say, C of W equals 1. And that was the claim in my sort of, description today of, up at the top, P knowing L such that H of L equals Z is implied by P knowing a W such that C of W equals 1. So, if the prover knows W such that C of W equals 1, the verifier is convinced it knows, the L such that H of L equals Z. Okay, so this is how it works. Well, first I'll tell you a straw man that works, but is like not satisfactory in terms of costs, which is, first the prover just literally sends W to the verifier. Sorry, maybe so. The prover sends to the verifier W. Okay, and then, so that's step 1. And then step 2 is they just apply the GKR protocol. So V can check that. Again, I'm not really sure what's up with my writing today, but that C of W equals 1, right? So the GKR protocol works for circuit evaluation. It'll save the verifier work if the circuit is small depth relative to the verifier evaluating C on her own. So to save the verifier that work, they're going to use the GKR protocol for the prover to convince the verifier that indeed C evaluates to 1 on W. Okay. So the reason we don't like this is because of step 1. The prover just sent W explicitly to the verifier. Now there are 2 reasons we might not like this. One is once you're using advice bits, this witness could be huge. Like these general transformations from computer programs to circuit SAT instances, if the computer program runs in time t, the number of advice bits you might need in general to get a circuit of size close to t is itself linear in t. It's like, imagine the advice bits literally specify a step-by-step execution trace of a random access machine that applies the computation that the prover is claiming to have applied to L, the private input L. So even if the private input that the prover is claiming to know in the original application, like the preimage or whatever, is small, once you apply the chapter 6 front ends to turn it into a circuit SAT instance, now the witness W to the circuit might be big, even if L was small, because the advice inputs there might be so much advice inputs. So we're really, really not happy with the prover having to send the circuit SAT witness to the verifier. like once the prover does that, the verifier might as well, like check that C of W equals 1 on her own at that point, because W is like a significant fraction of the circuit, size itself. Once the verifier like receives W, it's sort of already spent as much time as it takes to check that C of W equals 1. Yeah, and I'm saying the idea of the checking at C of W equals 1 here, as someone just wrote in the whiteboard, is 1 just indicates accept. Like you're thinking of the circuit as sort of like checking the validity of this witness W, and 1 means accept, and something that's not 1 means reject. So that's one reason we don't like the prover sending the witness to the verifier. And another reason would be like zero knowledge, right? If this witness leaks information about the private input, and indeed it contains the private input as like a subset of it, then the verifier is just going to learn the private input, and that's a gross violation of zero knowledge. Okay, so the succinct arguments we gave in chapter 7, they avoid that. And the idea of them is to simulate this straw man sort of cryptographically, but without the prover like literally sending W to the verifier. Yeah, this is actually probably working better that Thor or someone is writing what I say, since I'm too incompetent to use the iPad properly. So this is how it works. So the only fact you need to understand about the GKR protocol to understand chapter 7 is that the verifier in the GKR protocol doesn't need to know anything at all about the input to the circuit, which in this case is W, except to evaluate the multilinear extension W twiddle at a single random input R. Okay, so what's going to happen is in the succinct argument is the prover is going to cryptographically commit to the multilinear extension W twiddle of W. Okay, and that means what that means is the prover sends like, and that for example, depending on what there are lots of different commitment schemes you might use, and these are called polynomial commitment schemes, and they're like the subject of roughly half the book. There are lots of ones available, but some of them, for example, this commitment would be just a Merkle hash, right? So like the commitment itself is just one hash value. In others, the commitment is what's called like a Peterson hash. So that's one cryptographic group element. So the commitment is really tiny. It's like one hash value, one group element, something like that. And it sort of cryptographically binds the prover to the witness, or more precisely, the multilinear extension polynomial of it, which means once the verifier has in its possession the commitment, the prover can't go and like change the witness. In particular, like you would totally lose soundness of the protocol if the prover could learn R, the point at which the verifier needs to evaluate W twiddle, and then change W twiddle based on that. At that point, it could choose a different, if it could choose a different polynomial that agrees with the W twiddle it sort of was supposed to have committed to at R, but like disagrees elsewhere, right? Like then the verifiers, they're going to look the same at R, but not be the same. So you're going to soundness is just totally out the window. So yeah, so this is the protocol sort of proceeds then in like 3 steps, I guess. So I'm going to write this out, and then Thor or whoever else is helping me out can rewrite it legibly. And by maybe next week, I'll figure out what's wrong with my browser. So in step 1, the prover sends the commitment to W twiddle. So I'm going to write com W twiddle is what gets sent to the verifier. Again, think of that as like maybe just like one hash value or something. Sorry that that's like illegible. Okay. In step 2, the prover and the verifier run the GKR protocol. Again, apologies for this. Run GKR. I missed the K. Run GKR to check. This is like worse than my hand. Maybe I should just use my hand. Run GKR to check that C of W equals 1. Remember, like, I guess another thing I haven't said today, although I said it previously in previous sessions, to run the GKR protocol, the verifier doesn't need to know anything at all about the input W to the circuit until the very, very end of the protocol, at which point it only needs to know W twiddle evaluated at a random point R. So so I can say, you know, run GKR to check that C of W equals 1. And your initial reaction might be, well, how can they do that? The verifier doesn't know what W is because it only has like one hash value that commits to W twiddle. The answer is the verifier in the GKR protocol does not need to know anything at all about the input as the protocol proceeds until the very, very end, at which point it only needs to know W twiddle of R. So the final step is to, you know, use the evaluation procedure of the polynomial commitment scheme to, you know, V like demands or requests or whatever you want to say. V requests W twiddle of R from the prover, and that what the prover, these polynomial commitment schemes, you know, they operate sort of in two phases. There's the commit phase, which was captured in step 1 of these 3 steps, and then there's the evaluation phase where the verifier can say, hey, tell me the committed polynomials evaluation at you know, this point R that I care about. Prover can come back and say, hey, here's the evaluation, and like, by the way, here's also proof, okay, that the evaluation I'm returning to you is actually like consistent. It's actually the real evaluation of the committed polynomial, you know, that I sent the commitment to. So the verifier will, you know, plug in, you know, in step 3, the prover's claim as to what is W twiddle of R, like into the GKR protocol's final check, and also check using the polynomial commitment scheme's evaluation procedure. It'll check that the evaluation proof, you know, that proves the validity of that evaluation. But it'll check that as well. Okay, so there's a question in the chat. Is it generally true that not sorry, that was an old question, which I'm not sure I answered that. So if we want to talk about that later, we can come back to it. What the new question is, what does W look like? I thought it was a set of field elements, but not the evaluation of some polynomial of some domain. Great question. Okay, so W itself is just a vector of field elements. It's like it's an input to an arithmetic circuit. Okay, which is just a, you know, a vector of field elements. The field is whatever field the arithmetic circuit is defined over. Remember, when we have this way of viewing, of taking multilinear extensions of vectors. So what we do if we have a vector of length n, so if the vector W, again, apologies for the writing, if the vector W is an element of field to the n, so this incomprehensible symbol is supposed to be the is an element of symbol. Thank you. Okay, yeah, I'm just going to say this verbally, and Thor, you can write this out, I hope. So we interpret W as a function mapping 0, 1 to the log n to f. To f being the field. Yeah. So right, we just think of this vector W of length n as the list of all evaluations of a function over domain 0, 1 to the log n, right? Because there are n vectors in 0, 1 to the log n. So a function with that domain has n evaluations. So we're just viewing the vector W as the list of those. Okay, and now for any function from 0, 1 to the log n to field, there is a unique multilinear extension polynomial W twiddle of that function. So W itself, like, is just a vector of length n. It's an input to an arithmetic circuit that takes n inputs. But it makes sense to talk about its multilinear extension, at which point you are then thinking of the vector as the evaluations of some polynomial, namely W twiddle, over the domain 0, 1 to the log n, where now we're associating the field elements 0 and 1, that is the additive and multiplicative identity elements of the field. Yeah, so n in this scenario is just the number of inputs to the circuit. Okay, so like imagine, throughout this today's discussion, I've been thinking, using the example of, the prover is claiming to know a pre-image of some hash output where the hash function is SHA-3 or whatever. Okay, so you got in practice, you would feed, some computer program computing SHA-3 through a front end. That's going to spit out an equivalent circuit sat instance. Okay, I'm imagining, the initialization of SHA-3 has been fixed, which I think it has been. But anyway, that's so the circuit C has no public input. It's just the entire input to the circuit is, it's just like the claim pre-image L and advice bits of the advice field elements. Okay, so N in this scenario is just the length of the private input L plus the number of advice inputs, because that is the number of inputs to the circuit C that, the front end spits out. That's equivalent to, the original claim that SHA-3 evaluated at L equals what, the claimed output. Did that make sense?
Yes, thank you.
So, where does the login come from? I think I'm still not fully going back there.
Sure. Yeah. It's because the number of vectors in 0, 1 to the log n is n. So it's 2 to the log n, which is n. So again, to interpret, to talk about the multilinear extension of this length n vector w, right? What's happening is we're interpreting the vector as the list of all evaluations of some function that we can take a multilinear extension polynomial. So, what should the domain of that function be? Well, it should be a domain of size n, right? Because the vector has length n, and we want to interpret it as the list of all evaluations of the function. And in order for there to be a multi extension of the function, like the domain has to be 0, 1 to the something, right? So that's where log n is coming from. Like you need to, in order to take the multilinear extension of this function that has n evaluations, the domain of that function has to be 0, 1 to the log n, so that domain size has length n and is 0, 1 to the something. That something is log n.
Yeah, no, it makes total sense. I know what I mean to say. So it's like basically you have 0, 1, and if your n is 8, you have three kind of elements in that.
Yeah,
vector,
exactly.
right?
So
you have 8 total combinations.
Yeah. So if yeah, exactly. So if n is 8, then w twiddle is a 3-variate polynomial, right? If n is 2 to the 30, which is about 1 billion, then w twiddle is about a 30-variate polynomial. If n is a 2 to the 40, which I think is a trillion, it's a 40-variate polynomial. Yeah.
That is perfectly clear. Yeah, thanks.
Yeah. More questions? Okay, and then so the rest of chapter 7 just gives like a conceptually simple, I guess sort of as simple as they come, like polynomial commitment scheme. So the idea is, like, first it just describes Merkle trees, Merkle hashing. Merkle hashing will bind the prover to a vector. The chapter calls it a string. I don't know whether I should change that phrase to vector if it was confusing some people, but yeah, so the Merkle tree binds the prover to a vector, okay, but does not guarantee, does not give any guarantees about the contents of that. Okay, so you could imagine, like your first attempt at a polynomial commitment scheme might be, take the vector of all evaluations of, the multilinear polynomial the prover needs to commit to here, and just send the Merkle hash of it. This has multiple issues. One is, as I just said, the Merkle hashing will wind up binding, causing the prover to be bound to a vector, which we're interpreting as the list of all evaluations of a function, but it does not guarantee that function is a multilinear polynomial. So that's one problem, is like it doesn't actually bind the prover to a polynomial, it just binds the prover to a function, right? It binds the prover to a vector, which we're just going to interpret as all evaluations of some function. But we really need the prover to be bound to a vector that is interpreted as all evaluations of some function, and for that function to be a multilinear polynomial. So that's one issue. And then the other issue is just that the
Can I
number of
why
evaluations.
is that the case?
Why is that the case?
Yeah, why do I care that it's a function instead of a polynomial?
Yeah, so the soundness of the GKR protocol requires, like, uses the fact that the verifier gets an evaluation of the multilinear extension of the input, and it's not actually essential. What is it? Yeah, I mean, it's essential that for soundness that it be a multilinear polynomial that that evaluation is coming from. So if it was, for example, if it was just like a really, really high polynomial, like the soundness error of the protocol grows linearly with the degree of that polynomial. So that's one issue. So if the degree is huge, then you would need like an even bigger field. But actually, there are other reasons soundness breaks in the GKR protocol if that polynomial isn't multilinear. So yeah, it's just the soundness of the GKR protocol itself requires that the verifier evaluate the multilinear extension of the input, and so when the prover sort of commits to that input, the verifier is going to need an evaluation of the multilinear extension of it. So you need a guarantee that the polynomial that from the cryptographic commitment scheme that the argument system verifier is going to get an evaluation of, you need it to be multilinear for GKR soundness.
Yeah, okay, thank you.
Yeah, so that's one issue with just using a Merkle tree. The other issue is, which actually can't really be removed, because the commitment scheme given in chapter 7 is not practical for this reason, is the number of evaluations of W twiddle is like massive, right? It's like field size to the log n, right? So like even if your field size was 3, which is way too small for any soundness to hold, 3 to the log n is already like super linear in n, like n to the 3/2 or something, right? So if your field size was 100, to the log n, log base 2 of n is going to be insane. So yeah, so the polynomial commitment schemes people actually use don't actually work this way. Like the prover does not simply commit to like all evaluations of W twiddle. It does other stuff, so we'll see that in like later chapters. But let's not discuss the efficiency issue further. Let's discuss, and then we'll be done for the day, how you address the first issue, which is like a soundness issue, not an efficiency issue. Like how do you actually make sure the prover is bound to a multilinear polynomial and not just some arbitrary function? And the answer given in chapter 7 is you use what's called a low degree test. And this is just a way for the verifier to inspect, theoretically, asymptotically, conceptually speaking, very few evaluations of the committed function and get a high degree of confidence that those evaluations are consistent with a multilinear polynomial instead of just some arbitrary function, right? So these low degree tests sort of in practice are actually extremely expensive, and so what people actually use are interactive analog. Let's not worry about that right now. But anyway, so in chapter 7, it just sort of presents these low degree tests, like what the guarantee they give as some magical protocol that you're just not supposed to worry about the details of and how it actually is achieved. But the combination of Merkle hashing and low degree tests, that's enough to give you a polynomial commitment scheme, more or less. Because that guarantees not only is the prover bound to all evaluations of some function, but moreover that function is a polynomial with some technical caveats that's not worth getting into when I'm already over time. Yeah, so that is my summary of chapter 7. So I guess let's see if there are any more questions, but otherwise, I guess we'll proceed according to the ramblings I had before we started today about the best way to proceed in future weeks. Maybe I should, Thor, I'm free on Friday. It's getting close to the holiday weekend here, but it's fine with me. I guess we can discuss in the chat if we want another off week or whatever.
Sorry, you said that you are free next Friday?
Yeah, I just, like, if people want to meet a week from today, despite it being like the Friday of a holiday weekend, that is,
All right.
that's fine with me. Yeah.
Yeah, it's America Day. Yeah. Forgot. Yeah. Okay. I think I'd probably prefer to have a call next week. I think the question for me would be, do we want to head to chapter 8 or chapter 19 at the end of the book to kind of get a high level overview?
Yeah. So I guess my vote, based on the feedback from the last group, is head to the final chapter. But I certainly, if people have other feelings, I don't have strong, super strong ones.
Okay. I'm leaning head to final chapter, but I think I will put a, okay, so we got one vote for final chapter, and I think that final chapter is true, which I think is like an appropriate sampling for everyone's opinion. That was a joke. But it does seem like that there are at least 3 votes for final chapter now, which seem unopposed. So I think we might head to final chapter.
Great. It'd be good to get some feedback on that too, from readers who, haven't, are at the point that we are at. I don't think, no one has sent me feedback on that chapter, and it discusses deployed systems and things at a high level. So it's a good chapter to get people's thoughts on. Anyway,
Cool.
Okay, sounds good.
Yeah, then kind of putting a pause on implementation homework for a little bit until we kind of get back into the more cryptography direction. I guess optional cryptography homework, implement the awful snark that is a snark in chapter 7, but otherwise I think we're going to head to chapter 19.
Sounds good to me.
Cool. Yep. All right, cool. So meeting as usual next week. I don't have like an exact page count on what seems reasonable, but I recall that chapter 19 is kind of high level, so I think it probably seems reasonable to cover it in 2 weeks. I think it's like roughly a 15-page chapter, so maybe the first 8 pages of chapter 19.
Yeah, so it's not technical. So if people want to read more, of course it's optional, but also probably not the best to just say read 15 pages all at once. So optionally, just keep going. But yeah, sounds good.
Yeah. Cool. So it's actually shorter than I thought it was. It's 288 to 298. So let's just read it all.
Oh, okay, great.
Yeah.
Okay.
Right.
I can stick around for a little if anyone has questions, but otherwise, thanks as always, and I will see you on Friday.
Cool. All right. See everyone next week.
Bye.
Goodbye.
Bye.
Thank you. Bye.
Thank you.
So I have a quick question. Like, I see it mentioned quite a lot, argument of knowledge versus proof of knowledge. And if I understand correctly, this is just the difference between unbounded and bounded prover. Is that all there is to it, or is there any more kind of intricacies to that distinction?
The distinction between just like standard soundness and knowledge soundness?
Proof of knowledge and argument of knowledge.
Yeah, that's exactly the distinction. Yeah. And people will get like imprecise about this usage. I think sometimes they might not be careful. They might call an argument of knowledge. I sometimes maybe people are always careful, but yeah. Just as a general kind of rule, arguments always means computational soundness. So, and computationally unbounded prover could, break a crypto system and therefore, trick the verifier into accepting no matter what. And proof generally is supposed to mean information theoretic soundness, so security against even computationally unbounded provers. But yeah, you'll definitely have people refer to a snark proof, right? Like you'll say like a snark proof pi or something. And snarks are always arguments, right? In fact, the AR in snark means argument. So yeah, that's why I'm saying, like, you know, you have to be careful and like pay attention to context. Sometimes it can be difficult to tell what people are talking about. But yeah, as far as if people are drawing a distinction between a proof of knowledge and argument of knowledge, that is the distinction.
Okay, well, I heard CK proof thrown around quite a lot, so I assume this is very rare in practice, right? And people actually need zero knowledge argument.
Yeah. So everything people use in practice, it's an argument. I'm trying to think if there are any. I think what I'm saying is accurate. It's everything. It's so they'll say zero knowledge proof as really shorthand. Really, they mean zero knowledge argument. You know, again, like you cannot get succinctness. There is extremely compelling evidence, if you will, that you cannot get succinctness, meaning the proof length is shorter than the size of the witness. The trivial system where the prover just like sends the witness to the verifier, unless with information theoretic security. So whenever you have succinctness, it's always an argument. And in fact, I actually get annoyed even when I'm reading purely theoretical papers where the distinction between proofs and arguments is not clear. Sometimes I have to read, you know, deep into the paper to figure out what they're talking about, if they actually mean a proof or an argument, because they're vague about it. They just call it all like zero knowledge proofs, right? Yeah.
That's very useful.
Yeah, thanks for the question. It's a great question, and it can be confusing. You have to pay careful attention sometimes. Yeah.
I have made that. Now I know it's a mistake. I have used zero knowledge proofs myself.
Yeah, I mean, I want to be careful to. Yeah, I want to be careful to. You know, it's just like you know, the people are using shorthands that most other people that they're, you know, understand, but so I don't want to say like they're making a mistake, you know, like they're just using a shorthand, but and it and I find it frustrating. Like sometimes if people are talking about succinct, you know, argument systems, anything succinct, I have that context, so I always know. But once you start talking about non-succinct stuff, it really could go either way. Some of these papers are about non-succinct stuff, and they're using the proofs in this ambiguous way. So anyway, but they tend to be aware. You know, it's like they know they're being ambiguous. I think it's like an easier shorthand. So I hesitate. I just hesitate to use the word mistake.
Yeah, and I'm not sure if this question makes any sense, but is this at all related to to people relying on a random oracle model, and therefore like that being the argument versus, I guess, the opposite is the standard model, and then there being a proof? As I said, I'm not sure if this is.
No, that's actually, it's a good question. So it really depends precisely what you mean. So okay, so as a broader statement, you know, all snarks make some kind of sort of what's called a non-falsifiable. That's a technical term, assumption. Typically, it's one of random oracle or what they call knowledge of exponent assumptions, or is sometimes a combination of the two. So you know, these, and you can come up with people. You'll find people using like the, you know, proofs when they mean, you know, succinct arguments in all, for all of these snarks. You know, they'll say snark proof or whatever. So this isn't specific to the random oracle model. Now, if you are talking about protocols in the random oracle model, I believe I'm actually don't want to say this with 100% certainty, but I believe you might wind up with some settings where you literally you could have a protocol that is a proof. It is like information theoretically secure or something in the random oracle model, But if you were to deploy it in practice, you'd have to instantiate the random oracle with a concrete cryptographic hash function, and now it is an argument. I think that can happen. But that is, I don't think you're going to find yourself in that situation like all that often. So you don't have to, have that front and center in your mind, I think. If I was encountering something like that on a regular basis, I would confident answer about that to your question. But I think that could happen. Yeah. Does that make sense?
Yeah, that clarifies it a bit.
Cool. Any other questions? Okay, well, thanks for sticking around. I always appreciate the extra time, especially.
Thank you, Justin. Take care.
Many thanks. See you next week.
See you later.
Thank you.